So a logical question to ask might be, where are these blocks, or even what are these blocks that we're discussing when it comes to blockchain? And what blocks really just refer to is packaging a set of transactions occurring on the network into a group. We'll talk a bit about consensus and the process by which a network of nodes comes to agreement about what transactions are valid. But essentially, rather than engaging in that iterative process for every single individual transaction, they're done in batch for a bit more efficiency. And the other critical component of the block is the hash of the previous block. This is essentially what chains one block to another, giving us a blockchain. And that hash is essentially the cryptographic output of taking the input being the transactions in the block run through a cryptographic algorithm. It's a one-way function. For any given input, you will always get one and only one output out of these mathematical algorithms. And the properties of these algorithms are such that if you change even the smallest part, even one tiny part of the input going into the algorithm, you'll get a drastically different and fundamentally changed output, a different resulting hash, making it very apparent that something had been changed. Which is how if we have our block number 3 and someone hands us a block number 2 and we want to verify it's the block that goes with our block number 3, we can run that block through the hashing algorithm and confirm and compare its hash to the hash that we have embedded in our block number 3, and therefore validate the chain. In addition to using cryptographic hashing to confirm one block of the chain to the next, it can also be used to efficiently confirm the contents and structure of transactions within those blocks in what is frequently called a MERKLE tree. Hashes from multiple transactions can be combined and then rehashed, and then those branches, as they're called, can be combined and rehashed again, leading up to what's called a root. And remember, as we said, a hashing algorithm will give one and only one output for a given set of inputs. So this becomes powerful because to confirm that a transaction is, for example, in a given block, you need only the hashes of those transactions in order to rebuild the various branches and ultimately replicate the MERKLE root, which can then be compared and verified against what is shown in the block. So with a relatively small amount of data, not needing all the details of the transactions in those blocks, you can run a quick verification process. And with that, you should hopefully be building a better intuitive sense now of what we mean when we say blockchain. In many ways, we can think of blockchain as really being a type of database. And this database takes the form of a ledger. It's a history of transactions, and it is distributed in a peer-to-peer network. And we've begun to explore how cryptography allows us to represent larger amounts of information in small, efficient hashes using these one-way algorithms. This gives us a very powerful and efficient tool for determining that we're in fact talking about the same information. And that's ultimately why you hear that blockchains are immutable. To produce those consistent outputs and hashes, nothing in the database can be edited or deleted, otherwise you'd produce this dramatically different output. This is part of what creates and provides the stability and security inherent in blockchain, that if anybody was attempting to manipulate the database, that becomes apparent and can easily be checked.